I'm going to make an argument that will sound pessimistic, maybe even depressing, but I think it's probably correct based on what we know about physics, biology, and the universe. Intelligent life is unlikely, extraordinarily, improbably, astonishingly unlikely. We might be alone in the galaxy. We might even be alone in the observable universe. And the silence we hear when we listen for alien signals, the deafening cosmic silence, might not be because we're looking in the wrong way or listening on the wrong frequencies. It might be because there's simply nobody out there. I'm Richard Feynman, and I've spent my career thinking about the universe on the largest and smallest scales. And the more I learn, the more I appreciate just how special, how contingent, how fragile the emergence of intelligent life really is. Let me start with the Fermi paradox, because that's where this whole discussion begins. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. They were discussing flying saucers and whether extraterrestrial civilizations might exist. And Fermi asked a simple question: where is everybody? His point was this: the Milky Way galaxy is about 13 billion years old. It contains somewhere between 100 billion and 400 billion stars. Many of those stars have planets. We know this now from exoplanet surveys like Kepler and TESS. If even a tiny fraction of those planets developed intelligent life, and if even a small fraction of those civilizations developed space travel, the galaxy should be teeming with evidence of alien civilizations. They should have colonized the galaxy by now. They should have sent out probes. We should see their megastructures, their radio signals, their waste heat. We should see something, but we don't. We see nothing. The sky is silent. No signals, no visits, no artifacts, nothing. This is the Fermi paradox. If intelligent life should be common, why do we see no evidence of it? There are many proposed solutions to this paradox. Hundreds of them, actually. But I want to focus on one particular category of solutions, the one I find most compelling. Intelligent life is rare, vanishingly rare, maybe unique. Now, this goes against the Copernic principle, the idea that Earth is not special, that we're a typical planet around a typical star. And for a long time, I believed in the Copernic principle. I thought intelligent life must be common. The universe is so vast, the numbers so large, that intelligence must have arisen countless times. But the more I've learned, the more I've changed my mind. Let me walk you through the Drake equation, because it's a useful framework for thinking about this problem. In 1961, the astronomer Frank Drake proposed an equation to estimate the number of detectable civilizations in our galaxy. It looks like this: 99RAFP Nebraska FL, FI, FC. Let me break that down. 9 is the number of civilizations we might detect. Our star is the rate of star formation in the galaxy. FP is the fraction of stars with planets. 9 is the number of planets per star that could support life. 9 is the fraction of those planets where life actually develops. Phi is the fraction of life-bearing planets where intelligent life emerges. FC is the fraction of intelligent civilizations that develop detectable technology. And L is the length of time such civilizations broadcast signals. Now let's plug in some numbers. And this is where things get interesting and controversial. Our star, the star formation rate, is about 1 to 3 stars per year in our galaxy. We know that pretty well. FP, the fraction of stars with planets, is close to 1. Almost every star has planets. Kepler has shown us that the number of habitable planets per star is harder, but estimates range from 0.1 to 0.4. So roughly 10 to 40% of stars might have a planet in the habitable zone, the region where liquid water could exist. So far, the numbers look good. There should be billions of potentially habitable planets in our galaxy. But now we get to the really uncertain terms. Look, the fraction of habitable planets where life actually develops. We have one data point: Earth. Life arose here about 3.8 billion years ago, relatively quickly after the planet formed. Does that mean life arises easily, or did we get lucky? We don't know. Estimates for FL range from close to 1. Almost every habitable planet develops life down to 10 to minus 10 or lower. 100 orders of magnitude of uncertainty. Then there's phi, the fraction of life-bearing planets where intelligent life emerges. And this is where I think the real problem is. On Earth, life has existed for 3.8 billion years. For most of that time, about 3 billion years, life was nothing but single-celled organisms, bacteria and archaea. No multicellular life, no complexity, just single cells doing their thing. Then about 600 million years ago, something extraordinary happened. The Cambrian explosion. Suddenly, geologically speaking, multicellular life appeared. Animals, complex body plans, eyes, nervous systems, predator-prey, relationships. The diversity of life exploded. Why did it take 3 billion years for this to happen? We don't really know, but it suggests that the transition from single-celled life to complex multicellular life is not easy. It's not inevitable. It requires special conditions that may be rare. Let me dig deeper into this, because the timeline is crucial for understanding just how improbable our existence is. For the first 2 billion years of life on Earth, from about 3.88 billion years ago to about 1.8 billion years ago, there wasn't even any oxygen in the atmosphere. Zero. The atmosphere was mostly nitrogen, carbon dioxide, and methane. The oceans were filled with single-celled organisms doing anaerobic metabolism. Then around 2.4 billion years ago, something called the Great Oxidation Event occurred. Cyanobacteria, photosynthetic bacteria, had been producing oxygen as a waste product for hundreds of millions of years. At first, this oxygen was absorbed by iron dissolved in the oceans, forming rust that settled to the ocean floor. We can see these deposits today, banded iron formations, red layers in ancient rock, but eventually, all the iron in the oceans was oxidized, and the oxygen started accumulating in the atmosphere. This was catastrophic for most life at the time. Oxygen was toxic to the anaerobic organisms that dominated Earth. It was probably the first great mass extinction, but it also created an opportunity. Oxygen enables aerobic respiration, which is far more efficient than anaerobic metabolism. An aerobic organism can extract about 18 times more energy from glucose than an anaerobic one. This extra energy is what makes complex multicellular life possible. But even after oxygen appeared, it took another 1.8 billion years for complex life to emerge. Why? One problem was that oxygen levels fluctuated wildly. There was a period called the Boring Billion, from about 1.8 billion to 0.88 billion years ago, where oxygen levels were stuck at maybe 1 to 10% of modern levels, too low to support complex animals. It wasn't until around 800 million years ago that oxygen levels started rising again, and even then there was the snowball Earth period between about 720 and 635 million years ago when the entire planet froze over, possibly multiple times. Ice covered the oceans from pole to equator. Life barely survived. The Cambrian explosion, the sudden appearance of complex animals about 540 million years ago, happened only after all of these crises were resolved, after oxygen stabilized at high levels, after the planet thawed, after conditions became just right. And here's what disturbs me. There's no reason to think this sequence is inevitable. Oxygen production by cyanobacteria. The Great Oxidation Event surviving the snowball Earth. These were contingent events. They could have failed to happen. Earth could have remained a planet of bacteria forever. And then even after complex life emerged, it took another 600 million years for intelligent life to appear. Think about that timeline. Out of 4.5 billion years of Earth's history, complex life has only existed for the last 600 million years, about 13% of the time. And intelligent technological life has only existed for a few tens of thousands of years. About 0.007% of Earth's history. For 99 was 0.99% of Earth's existence. There was no intelligence, no one to ask questions, no one to do science, just bacteria. Then eventually plants and animals living and dying and evolving, but never thinking, never wondering, never knowing. Now let me talk about the evolution of intelligence itself, because this is another massive bottleneck that most people don't appreciate. Intelligence is not an inevitable outcome of evolution. It's not even obviously advantageous in most ecological niches. Consider dinosaurs. They dominated Earth for about 165 million years, far longer than mammals have existed. And in all that time, with all those species, with all that evolutionary innovation, not one dinosaur species developed anything approaching human-level intelligence. Some dinosaurs had large brains relative to body size. Some were social. Some used tools in rudimentary ways. But none of them built cities, created language, or developed technology. Why not? Because intelligence is expensive. A human brain uses about 20% of the body's energy budget despite being only 2% of body mass. That's an enormous metabolic cost. And for most of evolutionary history, that cost didn't pay off. Being a successful predator doesn't require intelligence. Sharks have been extremely successful for 450 million years with relatively small brains. Being a successful herbivore doesn't require intelligence. Grass has conquered huge swaths of the planet without a single neuron. Intelligence only becomes advantageous in very specific ecological niches. Niches that reward problem-solving, tool use, social cooperation, and long-term planning. On Earth, that niche was occupied by early hominids in Africa. Savanna-dwelling primates who faced variable environments needed to hunt cooperatively and benefited from making tools and sharing knowledge. But that's one lineage. One group of species out of millions of lineages that have existed on Earth, only one, our lineage, developed high intelligence. Crows are intelligent, octopuses are intelligent, dolphins are intelligent, but none of them developed technology, none of them created civilization. And here's something even more sobering. Consciousness itself, subjective experience. The feeling of what it's like to be something we don't even know if it's necessary for intelligence. It's possible to imagine intelligent behavior without consciousness. Philosophical zombies, as they're called, entities that behave intelligently but have no inner experience. We don't know when consciousness emerged in evolutionary history. Did the first animals have it? Do insects have it? Do fish? We don't know, and we don't know if consciousness is a necessary prerequisite for the kind of intelligence that builds civilizations. All of this adds layers of improbability on top of improbability. Out of billions of species that have existed on Earth, only one has developed technology. Only one has built cities, written language, done science. One species out of billions. The biologist Ernst Mayr argued that this shows intelligence is not an evolutionary inevitability. Most species do perfectly fine without it. Intelligence is metabolically expensive. It requires a big brain, which requires a lot of energy. And for most of evolutionary history, intelligence wasn't particularly advantageous. Mayer's conclusion was that phi is very small, maybe tenuous, 9 or smaller. If that's right, then even if every habitable planet develops life, intelligent life is still extraordinarily rare. Now let me tell you about some recent work that makes the picture even blearer. In 2024, two planetary scientists, Robert Stern and Terra Scaria, published a paper proposing that the Drake equation is missing two crucial terms. They argue that plate tectonics and the presence of both continents and oceans are essential for intelligent life to develop. Plate tectonics, the slow movement of crustal plates on Earth's surface, does several important things. It recycles carbon between the atmosphere and the Earth's interior, regulating climate over geological timescales. It creates diverse environments, mountains, valleys, coastlines that drive evolution. It may have played a crucial role in the Cambrian explosion by increasing oxygen levels in the oceans. And crucially, plate tectonics requires specific conditions. The planet needs to be the right size, large enough to retain internal heat, but not so large that the crust becomes too thick to move. It needs liquid water to lubricate the plate boundaries. It probably needs a large moon to stabilize its rotation and create tides. Earth has all of these. But how many other planets do Stern and Gary estimate that the fraction of habitable planets with significant continents, oceans, and long-lived plate tectonics is somewhere between 000 and 003 and 0.02. That's tiny. Even at the high end, that's only 2 planets out of every 1,000 habitable planets. When you multiply this into the Drake equation, the number of expected civilizations in the galaxy drops dramatically. Instead of thousands or millions, you get numbers close to 0, maybe 1, maybe less than 1, us alone. But let me add another layer to this problem that I find particularly troubling. Even if life exists elsewhere, even if it's common, detecting it is extraordinarily difficult. We've discovered over 5,000 exoplanets so far. We can measure their masses, their orbital periods, sometimes their atmospheric composition using transit spectroscopy. When the planet passes in front of its star, starlight filters through the atmosphere, and we can see absorption lines from atmospheric gases. This technique works. We've detected water vapor, carbon dioxide, methane, even sodium in exoplanet atmospheres. And in principle, we could detect biosignatures, gases that indicate the presence of life. The most obvious biosignature would be oxygen combined with methane. On Earth, these gases coexist in our atmosphere, in a state of chemical disequilibrium. Oxygen and methane react with each other. So the fact that both are present means something is constantly producing them. On Earth, that something is life. Plants produce oxygen through photosynthesis, and various microbes produce methane. Without life constantly replenishing these gases, they'd react away and disappear in less than 10 million years, an eye-link in geological time. So if we detect oxygen and methane together on an exoplanet, that's strong evidence for life. Not proof there are some abiotic processes that could produce these signatures, but strong evidence. But here's the problem. We haven't detected these signatures on any exoplanet yet. And the reason is technically most exoplanets we've discovered are either too large gas giants like Jupiter or orbit too close to dim dwarf stars, which makes spectroscopy difficult. The James Webb Space Telescope, launched in 2021, has the capability to detect biosignatures on small rocky exoplanets. We're finally reaching the point where we could detect life if it exists on nearby worlds. But we haven't. Not yet. And the longer we look without finding anything, the more the silence becomes meaningful. Now, even if we detected biosignatures, even if we found oxygen and methane on a dozen nearby exoplanets, that would tell us life exists. But it wouldn't tell us intelligent life exists. For that we need technosignatures, evidence of technology. And here the challenge becomes even more daunting. On Earth, human civilization has been producing detectable radio signals for less than 100 years. We started broadcasting radio in the 1920s. So our radio bubble, the expanding sphere of space where our signals could be detected, has a radius of only about 100 light-year years. The Milky Way is 100,000 light-years across. Our radio bubble covers about 1/1,000,000th of the galaxy's volume. If another civilization exists in the Milky Way, and they're at our technological level, and they started broadcasting at the same time we did, the chances of our radio bubbles overlapping are minuscule. And that's assuming civilizations continue broadcasting for a long time. We're already shifting away from powerful broadcast radio toward fiber optics, satellite communication, and directed beams. Our planet is becoming radio quiet. In another H100 red years, we might be essentially undetectable to CD-type searches. If most civilizations go through a similar transition, a brief radio window lasting only a century or two, then even if the galaxy contains thousands of civilizations, we might never detect each other because our radio windows don't overlap. There's also the problem of what frequency to listen on. The electromagnetic spectrum is vast. We've searched a tiny fraction of it at a tiny fraction of the sky for a tiny fraction of the time. It's like scooping a cup of water from the ocean and concluding there are no fish because you didn't find any in your cup. But despite these challenges, I think the null result is significant. We've been looking for over 60 years, we've surveyed millions of stars. If intelligent life were common, if civilizations were everywhere, we should have found something by now, a stray signal, an anomaly, something. The silence suggests that either civilizations are rare, or they're quiet, or they don't last long, or they're doing something we're not imagining. Now, you might object. You might say, Lenny, you're making eccentric assumptions. Maybe life doesn't need plate tectonics. Maybe it doesn't need continents and oceans. Maybe silicon-based life in ammonia oceans on a tidally locked planet around a dwarf star could develop intelligence just fine. And you'd be right to push back on that. We only have one example of life, Earth life. And extrapolating from one data point is dangerous. But here's the thing. We have to work with what we know. And what we know is that on Earth, intelligence required billions of years of evolution, specific geological conditions, multiple extinction events that cleared ecological niches, and a lot of luck. Maybe there are other pathways. Maybe intelligence can emerge without all these conditions. But we have no evidence of that. And in the absence of evidence, I think it's more reasonable to assume that the conditions that led to us are necessary or at least highly conducive. Let me talk about the Great Filter because it's relevant here. The Great Filter is a concept proposed by Robin Hanson. The idea is that somewhere between the formation of a planet and the development of a galaxy-spanning civilization, there's a filter, a barrier that prevents most attempts at life from succeeding. The question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, if the hard step is going from non-life to life or from simple life to complex life, then we've already passed it. We're past the hard part, and our future might be secure. But if the filter is ahead of us, if the hard step is surviving long enough to colonize the galaxy, then we're in trouble because it means most civilizations destroy themselves before they can expand beyond their home planet. Nuclear war, climate change, artificial intelligence gone wrong, pandemics, asteroid impacts. There are many ways a technological civilization could end. And here's what's disturbing. We have no evidence of civilizations that made it past the filter. The sky is silent. No one has colonized the galaxy. No one has left evidence of their existence that we can detect. That suggests that either the filter is behind us, meaning intelligent life is rare, or the filter is ahead of us, meaning we're doomed. I'm hoping it's the former. I'm hoping we're just rare, not doomed. But the data doesn't let us distinguish between these possibilities yet. Now, let me address the argument from large numbers. Because I hear this all the time, Lenny. The universe is so big, there are so many stars, so many planets. Even if the odds of intelligent life are tiny, there should still be lots of civilizations out there. The numbers are just too large. And I used to find this argument compelling, but I don't anymore. Here's why. Even if the universe is vast, the probabilities can be even vaster. If the probability of intelligent life arising on any given habitable planet is 10, the minus 21 in 100 billion, then even with billions of habitable planets, you'd expect fewer than one intelligent civilization in the galaxy. And we have no way of knowing if 10 US 20 is too pessimistic or too optimistic. It could be 10 to US 50, it could be 10 to minus 100. The point is, large numbers don't help if the probabilities are small enough. Let me give you an analogy. Imagine you're trying to win the lottery. The odds of winning are 1 in 300 million. Now you buy 1 billion tickets. Your odds improve, sure, but you're still unlikely to win. That's the situation with intelligent life. Yes, there are billions of planets, but if the odds of any one planet developing intelligence are tiny enough, those billions don't matter. Now, here's where this connects to my own work on the string landscape and the anthropic principle. And I think this perspective is crucial for understanding our place in the universe. In the multiverse picture, I've defended eternal inflation populating the string landscape. There are an incomprehensibly large number of universes, maybe 10 to the 500 different vacuum states, each realized infinitely many times in different pocket universes. Most of those universes are sterile, dead, unsuitable for life because the constants of nature are wrong. The cosmological constant is too large, or electrons are too heavy, or carbon can't form, or chemistry doesn't work. We exist in one of the rare universes where conditions allow for life. That's observer selection. We couldn't exist in any other kind of universe, so we necessarily find ourselves in a life-permitting universe. But here's the key question. Within our particular universe, with our particular laws of physics and constants of nature, how common is life? How common is intelligence? The multiverse explains why our universe has the right laws, but it doesn't guarantee that intelligent life is common within our universe. It's possible, maybe even likely, that even in a life-permitting universe like ours, the actual emergence of intelligent life is so improbable, so contingent on specific conditions and chance events that it happens only once per universe, or once per galaxy, or once per observable universe. The anthropic principle explains why we exist, but it doesn't explain why there should be lots of us. This is sometimes called the weak anthropic principle versus the strong anthropic principle. The weak version just says we exist in a universe compatible with our existence. The strong version says the universe must produce observers like us. I believe in the weak version. I'm skeptical of the strong version. And if I'm right, then the fact that we exist, that Earth has intelligent life, doesn't imply that intelligent life is common. It just implies that it happened at least once. Here, think about the lottery analogy again. If you win the lottery, that doesn't mean lots of other people won too. It just means someone won. We won the cosmic lottery. We exist in a life-permitting universe, on a planet, with the right geology, with the right history of oxygen accumulation and mass extinctions and evolutionary contingencies, in the right galaxy at the right time. That doesn't mean there are lots of other winners. It might just mean we got lucky. And this brings me to something I find both beautiful and terrifying. The observer selection effect might be masking our uniqueness. If intelligent life is incredibly rare, maybe unique in the observable universe, we would still expect to find ourselves in exactly the situation we observe. We would find ourselves on a habitable planet, in a life-pitting universe, surrounded by a vast cosmos that appears empty, because that's the only kind of place Snort's observers can exist. The universe could contain 1 million intelligent civilizations, or it could contain just one. And from our perspective, we couldn't tell the difference. We would observe the same thing either way ourselves, apparently alone, wondering if anyone else is out there. This is deeply unsettling to me. It means the data we have our own existence, the silence of the cosmos is compatible with both life, is common, and we are unique. We can't distinguish between these hypotheses observationally, at least not yet. All we can do is make estimates based on what we know about biology, geology, and the history of life on Earth. And those estimates, as I've argued, suggest that intelligent life is rare. Now, there's one more thing I want to talk about, the temporal aspect. The universe is about 13.8 billion years old. Our sun and solar system formed about 4.6 billion years ago. Earth is about 4.5 billion years old. We're relatively early. There are stars that formed billions of years before our Sunday. There could have been civilizations that arose billions of years ago. And if they arose billions of years ago, and if they developed space travel, they've had billions of years to colonize the galaxy. The galaxy should be completely filled with their descendants. But it's not. At least we see no evidence that it is. This is sometimes called the Hart-Tipler argument. Michael Hart and Frank Tipler independently argued that the absence of aliens on Earth proves that no extraterrestrial civilizations exist, because if they existed, they would have colonized the galaxy by now, including Earth. Now, there are counter-arguments. Maybe civilizations don't colonize,